Okay, let's take a look at this laser. What we have is something that is repetitive pulsed. Its primary wavelength is 532 nanometers, so it's visible light in the green. Looks like we put out 2.5 watts. It says greater than 2.5 watts, but you know what? We're going to use 2.5 watts, and I'll show you where even doubling the power probably won't matter. So 2.5 watts will be fine to use, and this is at 10 kilohertz. Pulse duration is less than 20 nanoseconds. We'll want to take a look at that and see if we want to use 20, less than, or does it matter. Also, the optimum frequency to run at is 5 to 10 kilohertz. So this is great. 10 kilohertz is where we generate our power out. So we'll look at 10 kilohertz and see if it matters if we run 5 kilohertz. What's the difference between 5 and 10? So I think kind of have an understanding of how the laser is going to run. The other thing is, at the output of the head, we have a beam diameter of 2 millimeters and no divergence information. So we'll talk about how we'll handle that. First, let's go see if this 20 nanoseconds really makes, what do we want to do with the 20 nanoseconds pulse duration. So let's look at the standard. We're going to look down in here, 500 to 700 nanometers. You'll notice that from 10 picoseconds to 5 microseconds, the MPE is the same. It's 2 times 10 to the minus 7th joules per square centimeter. So you see, we could use 20 nanoseconds, we could use 1 nanosecond, we could use 2 microseconds, and it won't matter. The MPE is constant over a huge range. So what we'll do for this analysis is we'll just throw 20 seconds in there. Okay, so let's go back to the analysis. We have a wavelength of 532. It is repetitive pulsed. We have an average power of 2.5 watts. We have a pulse duration of 20 nanoseconds. Let's start with a repetition rate of 10 kilohertz. We know our ANSI default, quarter of a second. We're going to stick with that. We have 2 millimeter beam diameter. Now here is, we don't have the information for divergence, so what we're going to do is we're going to put 1 in for m squared, and this produces our theoretical limit for our divergence. In other words, the smallest or worst case divergence we can have. Alright, so with this information in, we have enough to determine what OD we want. And it looks like 3.5 is our worst case. We have a 2 millimeter beam diameter going through a 7 millimeter aperture. So we're going to have 100% transmission through the limiting aperture. So even if we put our observer out, let's say 10 meters, we're going to see that it's still the same OD. So we can put this really at 0. It's 3.5. That means we're going to round up to 4. Now, what we want to know is, does it make a difference if we use 5 kilohertz? Right. You'll see, yeah, it makes a little bit of difference, doesn't it? And it's because it's going to make the MPE a little more restrictive in this case. Okay, and it's or not more restrictive, it's putting more energy into each pulse, so it gets a little more restrictive. So let's use 5 kilohertz in this case, but you'll notice it's still only 3.8. We're still rounding up to an OD of 4. So at 10 kilohertz, we have an OD of 3.5. We round up to 4. 5 kilohertz, we have an OD of 3.8. We round up to 4, so we'd still be buying an OD of 4. And you can, let's go back and take a look at this one more time. You'll notice this is where the MPE is staying the same, but what's going on here is the energy per pulse, which is driving up the peak power, changes when we change repetition rate. Okay, so that's what's making this repetition rate a little more hazardous, and we're still saying it's delivering 2.5 watts of average power, which we're not sure of. So we know for a fact that worst case, how we're looking at this, we need an OD of 4. What happens if we were to double the power and we go to 5? Well, you'll notice it goes to 4.1. This would probably not be realistic for in this case, nor at 5 kilohertz. At 10 kilohertz, if we doubled the power, you'd see we're at 3.8. We'd still be at an OD4. I doubt if the laser generates 2.5 watts at 5 kilohertz. That's the reason they spec'd it at 10. Okay, so if we stick with 10 kilohertz here, doubling the power would still be at an OD of 4. Okay, now let's look at the diffuse real quick. We have and we'll keep this power in here. Let's come over here. We'll assume diffuse is telling us what happens if the beam hits one time and scatters. So what we have here is a 4/10 of a meter scatter hazard. So 4/10 of a meter, that's 40 centimeters. That's 15 inches. So once this beam hits a surface and scatters, it's only a hazard for 15 inches. So if I was looking at an enclosure and I see a little green light, but I see that, well, the beam has to take at least one and probably more than one bounce before it gets to some of the cracks or openings in an enclosure that might be, near the floor, then you don't have a hazard there. Now remember that green light, you see green light better than any other light, right? So with this thing running 532, you can see a little bit of green light coming out of the enclosure possibly, but it's not going to be a hazard. Okay? All right, that should do it.